The next topic we will discuss are infinite series, and we will discuss whether or not, how to determine whether these series converge or diverge. Now, first of all, we have to think about how might you define a sum of an infinite number of things. So suppose we have, and we're going to use a lot of this summation notation, so it's capital sigma, and we'll start at a specific value, often 1, but sometimes 0. So n equals 1 to infinity of a sub n is the sum of a1 plus a2 plus a3, and this just keeps going forever and ever and ever. And what we do is we turn this into something we know. We can take this sum, this series, and turn it into a sequence as follows. And first we let S1 equal A1. S2 is A1 plus A2. S3 is the first three terms added together, A1 plus A2 plus A3. And in general, Sn is equal to a sum of the first n terms, A1 plus A2 plus all the way up to An. Now these are called partial sums. And this makes a sequence. We have the sequence of S sub n of partial sums. And what we say then is if this sequence of partial sums converges to sum L, then the series from n equals 1 to infinity of a sub n also converges to L. And also, if that sequence of partial sums diverges, then so does the series. So for an infinite series summed from 1 to infinity, the nth partial sum is given by a1 plus a2 plus up to an. And if this sequence of partial sums converges to S, then the series converges to S, and we say that the sum of from n equals 1 to infinity of a sub n is equal to S, and if the sequence of partial sums diverges, then so does the series. So let's figure out if this series converges or diverges. 1 over 2 to the n. So the first term, the first partial sum, is 1/2. The second partial sum is 1/2 plus 1/4, or 3/4. The third partial sum is 1/2 plus 1/4 plus 1/8, which is equal to 7/8. And from these first three partial sums, we can try to deduce a pattern for the nth term of the partial sum. Now it looks like the denominator is a 2 to the power of whatever partial sum it is. So the third term is 2 to the power of 3, second term 2 to the power of 4, so we have the denominator is 2 to the n. And the numerator is 1 less than the denominator, so 2 to the n minus 1, which if you divide both terms by 2 to the n is 1 minus 1 over 2 to the n. And thus the limit as n goes to infinity of 1 minus 1 over 2 to the n is equal to 1. So this sum converges and it equals 1. Another way to think about this is as follows. Suppose this is a distance of 1 unit and you want to walk the whole 1 unit. So first you go halfway, then you go half of the half, which is 1/4, and then you go half of the half remaining, which is 1/8, and then 1/16, 1/32, and when you add all these up, you should eventually get 1, and all those terms really are what's given here: 1/2, 1/4, 1/8, 1/16, etc. Now this next example seems like it's going to be really, really challenging, but let's just list the first few terms and see what happens. So first, when we input 1, we'll have 1 minus 1/2 plus our next term we get by inputting 2, and we'll have 1/2 minus a third. Input 3, and we'll have a third minus a quarter. And let's just say, so etc. That goes on forever. And notice how these terms cancel, these terms cancel, the 1/4 will cancel with the next thing. So the nth partial sum, S sub n, will be given by 1 minus 1/2, and then plus 1/2 minus a third, plus until the last term, which will be 1 over n minus 1 over n plus 1. And this term will cancel with the immediate previous term. These terms cancel. Everything in the middle cancels except for the first one and the last 1 over n plus 1. This is an example of something called a telescoping series. As you can, it's kind of like a telescope folds back into itself. Alright, so then you can find the limit as n goes to infinity of S sub n is equal to 1, and thus this series converges to 1. So the sum from n equals 1 to infinity of 1. Now what the heck does this mean? So what this means is we have 1 plus 1 plus 1 plus 1 forever and ever and ever. So S sub n, the nth partial sum, is 1 plus 1 plus 1 n times, which is the same thing as n times 1. And since the limit as n goes to infinity of S sub n is equal to infinity, this series diverges. Similarly, the sum of 2, same thing. S sub n will equal 2 plus 2 plus 2 n times, or 2n, and since the limit as n goes to infinity of 2n is infinite, this series also diverges. So, as I mentioned in a previous example, a telescoping series is one of the form where we have some kind of cancellation of terms happening. Those two cancel, these two cancel, the b4 would cancel with a positive b4 in the next term. So the first example we had of a telescoping series was pretty simple because of the fact that you already knew you had a fraction minus another fraction. Now we can use partial fraction decomposition to express this 2 over 4n squared minus 1 in that form also. So we'll have 2 over 4n squared minus 1. Now notice that 4n squared minus 1 is factors into 2n plus 1 times 2n minus 1. So that's the same thing as a over 2n minus 1 plus b over 2n plus 1. And if you find your partial fraction decomposition using the techniques we learned in the previous lesson, you'll have that a is 1 and b is negative 1, and we have 1 over 2n minus 1 minus 1 over 2n plus 1. So my series is the same thing as the sum from n equals 1 to infinity of 1 over 2n minus 1 minus 1 over 2n plus 1. Now let's find an expression for S sub n, the nth partial sum. So first, when we input 1, 1 over 2 minus 1 will give us 1 minus 1/3. When we input 2, we'll have 1/3 minus a 5th. When we input 3, we'll have a 5th minus a 7th, etc., until the last term when we input n, and we'll have 1 over 2n minus 1 plus 1 over 2n plus 1. And as you can see, everything will cancel except for the 1 and the 1 over 2n plus 1. And that should have, that should have been a minus right there. So the nth partial sum is given by 1 minus 1 over 2n plus 1. And the limit as n goes to infinity of that s sub n will equal 1. So thus this series sums to 1. Another common series is a series called a geometric series. And in order to make this formula work out a little bit more nicely, we're going to start this series at 0. So we have the sum from n equals 0 to infinity of a times r to the n, which is a plus a times r plus a times r squared, etc., where a is not equal to 0. This is called the geometric series with ratio r. And we are going to prove that if the absolute value of r is in between 0 and 1, this series converges to this particular formula. If r is equal to 1, we're going to have the sum of a. And so we already had examples like that, like the sums of the 2's and the 1's. And so if r is equal to both 1 and actually also negative 1, this series is going to diverge. So we're going to assume that r is not equal to plus or minus 1. So then the nth partial sum s sub n is given by a plus a times r plus a r squared plus up to a r to the n. And I'm going to take that sum and multiply it by r. So r s sub n will be ar plus ar squared plus up to ar to the n plus 1. And now, if I take s sub n and take away r s sub n, you can see that all these terms are going to cancel, except for the a minus the a times r to the n plus 1 power. And now on the left, I will factor out an s sub n. On the right, I'll factor out an a. So s sub n, the partial sum, is given by a times 1 minus r to the n plus 1 over 1 minus r. And what we now know is that if your r, when it's absolute valued, it's in between 0 and 1, then r sub n is going to go to 0. So thinking about, say, multiplying something like a half by itself repeatedly, 1/2, a quarter, an eighth, a 16th, etc., that's eventually going to go to 0. And thus, s sub n is going to go to a over 1 minus r. And if r is greater than 1, this expression right here, this r to the n plus 1, is going to get very large, and this series will diverge. Alright, so we have the sum from n equals 0 to infinity of 5 over 3 to the n. Now we can express that as the sum from n equals 0 to infinity of 5 times 1/3 to the n. So the formula that we have is this sum adds up to a over 1 minus r. And two things to note about that. First of all, it only applies if the absolute value of r is in between 0 and 1. In this case, it does. And the other thing is your sum has to start at 0. So we'll discuss later how to deal with things if your sum starts at something like 1, but just be aware that your sums must begin at 0, so we'll have to change them if they don't. And so in this case, the a is equal to 5 and the r is 1/3. So this series sums up to 5 over 1 minus 1/3. So 5 divided by 2/3, which is the same thing as 5 times 3/2, or 15/2. Now, in this series, A is equal to 1, and R is equal to 4/3. And since 4/3 is greater than 1, this series diverges. Express the following as a geometric series and find the limit. So I think it's easiest to express this as a sum from n equals 1 to infinity of 3 times 1 over 10 to the n. And let's just check. When we plug in 1, we'll have 3 over 10. Plug in 2, 3 over 10's 3 times 1 over 10 squared, which is 1 over 100. Alright, so now the question is how do we change that so that the sum begins at 0? So if I change this to n equals 0 to infinity, I have to change my exponent to n plus 1. And then I can write that as a sum from n equals 0 to infinity of 3 times 1/10 times 1/10 to the n. And that comes from exponent rules. If you were combining these, you would add the powers up to n plus 1. And now we can use our formula for the sum of a geometric series. The a is equal to 3/10. The r is equal to 1/10, and since that is in between 0 and 1, we are able to use the formula a over 1 minus r. So we'll have 3/10 over 1 minus 1/10. So 3/10 divided by 9/10, or multiplied by 10 over 9, which will equal 1/3. And that should make sense, as this really is another way of expressing 0.333 repeating. Alright, express the following as a series and find the limit. So we can think about this as 0.15 plus 0.0015 plus 0.00015, etc. And that's the same thing as 15/100ths plus 15 over 10,000, etc. So a sum from, let's just say, n equals 1 to infinity, 15 times 1 over 100 to the nth. So 100 to the first is 1 over 100. 100 squared would be 1 followed by 4 zeros. Now let's just change that so it sums from 0. 15 times 1 over 100 to the n plus 1. So in the end we'll have n equals 1 to infinity, 15 over 100 times 1 over 100 to the n. So using our formula, this will sum to 15 over 100 divided by 1 minus 100th, or 15 over 100 multiplied by 100 over 99, which is 15/99ths, or dividing the top and bottom by 3, 5 over 33. Find the sum of this geometric series. So one difference here is that this sum is alternating. The first term is positive, the second term is negative, so we have to have a negative sign someplace. So I think we can say sum from n equals, let's try to start this one at 0. So first of all, let's think about, take out those 5s. We'll have 5 minus 5 times 2/3 plus 5 times 4/9 minus 5 times 8/27. And if you look at it that way, it's a little bit easier to see the pattern, to see how here in the first term we have 2/3 to the 0, i.e. 1, 2/3 to the first, 2/3 to the second. So the a is 5 times negative 2/3 to the n. And in this case, we already have the sum beginning at 0, so we can go ahead and apply our formula. So we'll have 5 over 1 minus negative 2/3. So that will be 5 over 5/3, which is the same thing as 5 times 3/5. So this geometric series sums to 3. Now, is this series convergent or divergent? It's not very easy to tell as is, so let's try to manipulate it a little bit. So we'll have the sum from n equals 1 to infinity. Now, first of all, 2 to the 2n can be written as 2 to the 2 to the n, and then 3 to the 1 minus n can be written as 3 to the first times 3 to the negative n. So this is the same thing as the sum from n equals 1 to infinity, 3 times 4 to the n times 3 to the negative n, or a sum from n equals 1 to infinity of 3 times 4 to the n over 3 to the n, which is the sum from n equals 1 to infinity of 3 times 4/3 to the n. Now, we could change the indices so that this sum began at 0, but that wouldn't change the fact that the r is equal to 4/3, which is bigger than 1. And since that ratio, that r is 4/3 and it's greater than 1, it doesn't matter if we change our indices, this series is going to be divergent. Now here's a real-life example of series. So we have a ball, and it's dropped from a height of 10 feet, and it begins bouncing. And the height of each bounce is 5/8 of the previous bounce. Find the total vertical distance traveled by the ball. So on the first go, the ball falls that 10 feet, right? And then it goes up and down, up and down, up and down, where each distance up is 5/8 of the previous distance. So the distance, we'll say d1 is equal to 10. The distance on bounce 2, which I'm going to call d2, is equal to 10 times 5/8 plus 10 times 5/8. So that's this up and this down. D3 will equal 5/8 of the previous bounce, so 10 times 5/8 times 5/8 again, so that's 5/8 squared, plus 10 times 5/8 squared. So notice that D2 is then 20 times 5/8, and D3 is 20 times 5/8 squared. So in general, dn is going to be 20 times 5/8 to the n minus 1. So the total distance will be given by 10 plus a sum. We'll say from n equals 1 to infinity of 20 times 5/8 to the nth power. And doing a renaming of our indices, we'll have 10 plus the sum from n equals 1 to infinity, n equals 0, 20 times 5/8 to the n plus 1. So that will be 10 plus the sum from n equals 0 to infinity, 20 times 5/8 will be 100/8 times 5/8 to the n. And since 5/8 is less than 1, we can apply the summation formula for a geometric series. We'll have 10 plus 100/8 divided by 1 minus 5/8. So that's 10 plus 100 over 8 times 8 over 3, which adds up to 130 over 3 feet. Alright, so now we have a couple more theorems, and then we'll be done for the day. So the limit of the nth term of a convergence series says that if a series converges, then the limit is 0. So what we're going to do to prove this is assume that the sum from n equals 1 to infinity of a sub n, which is the same thing as the limit of the partial sums, is equal to some number L. And then notice that the nth partial sum is given by the n minus first partial sum plus the nth term. And the limit as n goes to infinity of f sub n is equal to L. So the limit as n goes to infinity of the n minus first partial sum also has to be L. And this tells us, if we limit everything in this expression, the limit as n goes to infinity of s sub n has to equal the limit as n goes to infinity of s sub n minus 1 plus the limit as n goes to infinity of a sub n. And this is L, and this is L. And when we solve for the limit as n goes to infinity of a sub n, we take away L from both sides, and this implies what we needed to show. The limit of the terms is 0. So just be aware that what this says is if the series converges, then the limit is 0. Not that the limit being 0 means it converges. It's what's called a necessary but not sufficient condition. It means it has to happen if your series is going to converge, but if it does happen, it doesn't mean the series converges necessarily. So here's show that the converse of the theorem above is not true by showing that this harmonic series is divergent. So this is a little tricky to prove, but here's how we're going to do it. We're going to find the values of the partial sums at powers of 2. So the first partial sum, S1, is 1. S2 is 1 plus 1/2. S4 is 1 plus 1/2 plus 1/3 plus 1/4. And what you should notice is that 1/3 plus 1/4, this is greater than 1 plus 1/2 plus 1/4 plus 1/4, because 1/4 is less than 1/3, and that's the same thing as 1 plus 2 over 2. And the eighth partial sum, that'll be 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 and plus 1/8. And we discussed the fact that this 1/3 plus 1/4, that's greater than 1/4 plus 1/4. And this last bit is greater than a whole sum of 4 1/8. So 1/8 plus 1/8 plus 1/8 plus 1/8, which is equal to 1 plus 3 over 2. So what this tells us is that the nth partial sum of 2 to the n power is equal to, is greater than 1 plus n over 2. So you see how this is 2 to the first, 2 to the second, 2 to the third, and this is a 3, 2 to the second, that's a 2. So it's looking at a very specific set of partial sums at all the powers of 2. And since all these powers of 2 are greater than this, and the limit as n goes to infinity of 1 plus n over 2 is infinite, that series has to be divergent, because the sequence of a subset of the sequence of partial sums diverges. So if all these intermittent, and increasing values are greater than this, and this thing that's less diverges, so does the greater thing. The converse of that theorem above is true. So our theorem says that if the series a sub n converges, then the limit of the terms is 0. And if this is true, then the converse is true. And the converse is that if the limit as n goes to infinity of the a sub n terms are not 0, then your series of a sub n does not converge. So use the nth term test for divergence to explain why the following series converge or diverge. So the limit as n goes to infinity of n squared plus 1 over 2n squared minus 5 is equal to 1/2, which is not 0, so thus the series diverges. What you can think about is this means effectively what you're doing is adding up, eventually, once you get large enough, is adding up 1/2 over and over and over and over. And as we discussed with this series of like 1 plus 1 plus 1 plus 1, or 2 plus 2 plus 2 plus 2, that those diverge. And similarly, if we find the limit as n goes to infinity of 3n factorial over 5n factorial minus 2, we can divide top and bottom by n factorial, and we'll have 3 over 5 minus 2 over n factorial, which is 3/5. So, which is not equal to 0. So, thus, by the test for divergence, the series diverges.